All right, we're supposed to start with optical isomerism. So optical isomerism, first of all, is another type of stereoisomerism. Okay, for us, a background, a little bit of background, what we have been doing previously. Okay, so we started off with isomerism, and since we know the definition, the very definition of isomerism, that it has the same molecular formula but different structure, that definition actually belongs to a certain type of isomerism. Now we have many types and subtypes of isomerism in A levels. So starting off with this definition is actually the first type of isomerism itself, which is structural isomerism, in which the molecular formula is same, but the structure or structural formula is different. Now that is structural isomerism. This is the first type itself, and this is further bifurcated into three types: position, functional group, and chain isomerism. Position isomerism is simple. It's all about the location of the functional group. The functional group may be present at a different carbon atom in the same compound. It would be then position isomerism. If the isomerism is based upon two entirely different functional groups, like in this case, one of them is alcohol, one of them is ether, but they have the same molecular formula but different structure, that would be functional group isomerism. And lastly, chain isomerism is the isomerism in which the structure of the carbon skeleton or the carbon parent chain or the number of carbon branches is different for different structures or for different isomerism, hence that is known as chain isomerism. Now, position, chain, and functional group isomerism are all themselves type of structural isomerism, for which we had the definition we did back in IGCSE, that the molecular formula is same, but the structural formula or structure is different. Now, there is another way we define isomerism, and that is the second kind of isomerism. That is stereoisomerism. Compounds have the molecules, same atoms are bonded to one another, which means molecular formula is same, which means structure is also same, but which means that the atoms in space for that structure will have a different arrangement. So that means molecular formula, same, structural formula, same, arrangement of atoms in space, different. For that, we further categorize it into geometrical isomerism and optical isomerism. By the way, geometrical is also known as cis-trans isomerism. Now, geometrical or cis-trans isomerism is all about carbon-carbon double bonds and how they can't have free rotation, and the atoms in space, if are rotated, will have the other type. As the name suggests, this one has the two types, cis isomers or trans isomers. When they're arranged diagonally around the carbon-carbon double bond, something like this, around the main diagonals, or we say that across the carbon-carbon double bond, okay, they're positioned across the carbon-carbon double bond, we call them trans isomers. Now, if they are not across the carbon-carbon double bond, if they are on the same side of the carbon-carbon double bond, either up or down, that means they are cis isomers. Okay, that's how we define cis and trans isomers. I explained what kind of different cis trans isomerism may exist. I explained also an example of what is usually used to confuse A-level students and make different MCQ questions. Okay. I also explained that then how it would become a cis and trans isomer if there are no double bonds in their cyclic structures. Now, cis trans isomerism also exists in cyclic structures like this, or though this is the same example. It's just been explained in detail by this kind of structure. So it gives us the idea for this. Also, another example for cycloalkanes, the example for cis and trans isomerism. Now, the last subtype of isomerism, this optical isomerism is itself a type of isomerism, a type of stereoisomerism, actually. So we are going to go with this last type today. Now, a little bit of some prerequisite knowledge before we actually start optical isomerism. If a molecule contains a carbon atom that is bonded to four different atoms or group of atoms, it can actually form uh, optical isomers. Now, for this specific one, let's consider the case. If you take a look at this diagram, you would notice this carbon is bonded to H1, OH2, CH3, 3, and COOH or CO2H, 4. This is bonded to 4 different atoms or group of atoms. We can describe this specific carbon atom as asymmetric carbon atom, but a more important name for this one would be chiral carbon. This one would be considered as chiral carbon. This can also be known as chiral center, which is mentioned over here. Now, if there are 2 of these kind of structures, and if we pass a mirror plane in them, take a look at these structures. And now I'm going to erase this to make sure that we can explain this. Now, if you notice, I'm going to use these colors. Same group over here, same group over here, same carbon atom over here, another same set of group over here, and same group over here. Maybe it's atom or group of atoms that we can consider. You'll notice the whole structure is same. It's just that we're talking about a carbon plane right in between and the mirror plane right in between. Now, when you stand in front of the mirror, the right and left of you and your image are actually exchanged. Your right hand becomes mirror right, mirrors left, and your left becomes mirrors right. Now take a look at this. This actually acts as a mirror image. If I erase all of these and explain you with the help of, take a look at this. This is the carbon on its, if we say on its left, and this one is right, notice this would switch as this one's now left and this one's now right. But the whole structure is still the same. Dotted, dotted, straight, straight, wedged, wedged, straight, straight. So just the rights and lefts have been exchanged. This is known as a mirror image. Then these two structures will be known as enantiomers. Yeah, we have been using the word isomers all along. We have been using the word isomers lately, but now I am going to explain the major difference to you. And in order to explain that difference, I'm going to take you a little bit back into the start of isomerism. Now, when we were defining isomerism, for example, this is the specific example we considered for position isomerism. We said that these are all isomers. This is the word we have been commonly using, isomers, no matter how many structures we're talking about. Now, if you remember, this was 1,2 isomer, this was 1,3 isomer, this was 1,1 isomer, sorry, not like this, and this was 2,2 isomer. Now, I have already explained how 2,3 or 3,3 do not exist. Now, it's okay if we call them isomers. If you want to be a little bit more specific, you can call them position isomers. Okay, but we still use the word isomers. That's good enough for them. If I keep moving to the next type, again, we call them isomers. If you want to be specific with these words, you can call them isomers. Both the structure are isomers to one another, but you can call them functional group isomers if you want to be specific in your answers to your theory paper. We're specifically talking about paper 2. Okay, but we still use the word isomers. Now here, we also use the word isomer. Isomers for one another, what we can use is we can specifically say they are chain isomers to one another. Okay, because we understand they have the same molecular formula, but different structure. Now, this is the common term we have been using for structural isomers. Now, let me take you to stereoisomers. When it comes to stereoisomers, something that is a part of their names, cis isomers, trans isomer. That's a very good way of representing symmetrical or cis-trans isomerism. Now, when you come to this, you'll understand that the isomers are named a little bit differently as per their nomenclature rules. Now, for optical isomers, we don't even use the word isomers. Okay, we don't use this word. What do we use? We use the word enantiomers. Okay, that's the point I wanted to make. And I hope I am clear with this point. Not just that, there are more things that we need to explain. Now, when there are two different optical isomers, we call them enantiomers. They are actually mirror images of one another, and they cannot be superimposed. How? What is superimposition? Superimposition is when you put one structure on top of another, and you don't end up with the same atoms on top of another. How do you do this? Let me explain. I'm going to pick up this structure and I'm going to put this structure on top of this one. So I'm putting this carbon right next to this carbon. Okay. And then what would happen is that we'll have a wedge, a little bit of wedge over here with CO2H. Now, this is not on top of this one. Okay. And over here we have OH. Over here we have H. And over here we have CH3. Now, if I put one structure on top of another, you'd notice that the atoms are not same on top of one another. The right and the left have been switched. So they cannot be superimposed. We use the word non-superimposable. And non-superimposable is actually a property of enantiomers. And enantiomers actually come from chiral carbon and chiral center. So there are multiple ways of telling an optical isomer. So these are somewhat like the prerequisite. In order to be an optical isomer, there has to be a chiral carbon, right? This would be a chiral carbon, which would be the chiral center of this atom. And then in order to be enantiomers, they should be mirror images of one another. They should be non-superimposable, okay? And that's how they'll become optical isomers or enantiomers. Make sense? For these, I usually also suggest some YouTube videos. If you see, you look at it from a three-dimensional perspective, all I've been doing is teaching you two-dimensionally, which is a little bit difficult to form a good piece of or sense of imagination. Yeah, the students that are usually good with imagination, they can come up with an image in their mind, but sometimes if you're not able to form the proper image in your mind, I suggest that you do take a look at a few 3D YouTube videos. And I am going to actually refer you to a couple of videos. They won't take much longer. They would hardly take 5 to 10 minutes of your time, but they are going to give you a very good idea of superimposition, whether it is superimposable or non-superimposable. How do we explain with the help of daily life examples, one hand on top of another, talking about human hands, human face, human feet, or talking about some commonly usable stuff in everyday life. And then really after that, we come towards some chemical structures. And then it's easier to understand chemical structures because the previous examples are extremely relatable examples. They usually start explaining this kind of stuff with human hands. Since I'm not showing myself, I'm actually going with sharing the PDF of the book. This is a little bit difficult for me to show you how we start with the example of hands, okay? But the videos I'm going to refer you are going to help you greatly at managing an image in your mind about chiral centers, enantiomers, superimposition, whether it's superimposable or non-superimposable, right? Now, this pair of molecules are optical isomers. We actually refer them to as enantiomers. Trying to superimpose the two isomers is like to trying to superimpose your left hand on top of your right hand. With them both facing downwards, it can't be done. The thumbs will not be on top of one another. One thumb will be sticking out on the left, one thumb would be sticking out on the right. We commonly can do it as the first piece of experiment to explain the enantiomers and how they are non-superimposable. That's the example I'm talking about, which he gave as a caption of figure 14.24. Okay. I am going to assume that you understood it. If not, make sure that you do watch the videos I'm about to send you right after this class on WhatsApp, and that is going to help you a lot with the understanding of enantiomers. Let's move on. So modeling optical isomers, we actually use the modeling kits. The modeling kits are really easy to work with in labs, but here we are going to explain it a little bit more. Now, why are we stressing upon optical isomers so much? There are a few certain points related to, a couple of them related to physics and the rest related to chemistry that we need to understand before we move on with optical isomers. So optical isomers actually differ in their effect on polarized light. I hope you understand what plain polarized light means. Uh, Plain polarized light actually means light of one single wavelength. Normal light is unpolarized. It has actually a multiple set of wavelengths from non-normal light. Now, this is not just based on one wavelength. Well, we can always set up a good apparatus in physics to make sure that we work with only one kind of wavelength of light. Okay. It can be thought of as fluctuating electrical and magnetic fields. They vibrate at right angles to one another in every possible direction. Passing this unpolarized light through a polarizer actually results in a polarized light. What happens is that polarizer actually allows only one single wavelength of light to pass and it stops all the rest. Now, this vibrates only in one plane. A pair of optical isomers will rotate the plane of polarized light by equal amounts, but in opposite directions. One of them will rotate the plane of polarized light clockwise and the other one anti-clockwise. Now, this is the best part. We, as humans, did not know about the optical isomerism much later in the 19th century, by the end of the 19th century. So it was difficult to work with it. As I've given you the examples of medicine before, we were actually, we started synthesizing different molecules, and some of them had medicinal effects, and we were working a lot with medicine, but medicine never had a complete set of positive and negative effects at the same time. So medicine was actually affecting in a good way some humans, and for the rest, it wasn't working well. So we understood that there was something different with those molecules. Even when their whole structure was same, there was something different in depth. Now, this was the depth. Although the molecular formula of those medicinal molecules was same, their structure was same, the chiral centers actually didn't have the arrangement of atoms same. And because of that arrangement, their entire medicinal effect was different. I've given you examples for cis-12. There are examples that exist for optical isomers as well. Some optical isomers where one of the enantiomers is very good for health, the other one can be extremely negatively effective for the health. So moving on, um, organic molecules can contain more than one asymmetric carbon atoms, more than one chiral center. If there are two asymmetric carbon atoms, then each of the chiral centers will rotate the plane of polarized light. In this case, there would be four possible optical isomers. Now that's the possibility of 1, 1, 1, 2, 2, 1, 2, 2. All of those possibilities are there. As well as the straight and branch chain molecules, substituted cyclic molecules also have chiral centers in their ring structures. To decide whether the chiral centers are, we still have to find any carbon atoms that are bonded to four different atoms or groups of atoms. To look at this example, we need to come up with this. Okay, when you look at it, what do you understand? Now, remember, this is carbon, carbon. These all corners are carbon atoms. And of course, every carbon atom over here has one bond, two bonds, so there must be two hydrogen, like this, two hydrogen, like this, two hydrogen, then two hydrogen. Now, this one already has a different bond. So this would be hydrogen over here. This would be hydrogen over here, right? This is a substituted cyclohexane. Cyclo means the structure is cyclic. Of course, this is a cyclic structure. The first and last carbon are always bonded. Even if when you count the numbers different, count the carbon atoms differently, it would always be bonded. Hex means 6 carbon atoms. Since they're all singly bonded cyclohexane, substituted means they have some functional groups on top of them. This is what substituted cyclohexane word means. Now, in cyclohexane, all the carbon atoms are bonded to two hydrogen atoms. There is no chiral center, okay? Because same atom, same atom. Now, this is a huge hint for a lot of MCU questions that you are going to face in AS. Now, in paper one, they give you structures and they ask you to number the asymmetric carbon atoms, or what we call chiral centers or chiral carbons. Now, you can work with it in a very good way, in such a way that if you have something like this, now I'm going to erase all of it. If you have something like this, right, this portion, you can always clearly understand that if you have something like this carbon can never be chiral. Why? There are two atoms on this one which are same. And the first property we need from chiral carbons is that all four atoms or group of atoms has to be different. Take a look at this: hydrogen, hydroxyl, methyl, and carboxylic acid group. These are four different atoms or group of atoms. Only then this carbon is chiral. So if I go back to where I was, this gives you a pretty good idea how these carbon atoms 1, 2, 3, 4 are not chiral, can never be chiral. Why? Because they have two same atoms at them, two hydrogens, which means any carbon like this or carbon like this cannot be chiral. However, this may be chiral. It depends. Or this may be chiral. If all four atoms or group of atoms are different on this one, they may be chiral. But these two can never be chiral. Okay, so any carbon at the corner of a chain may never be chiral, whether it's singly bonded or it's doubly bonded. Again, a carbon in the center with just two simple bonds and two hydrogens can never be chiral again. This is a very good hint for the students to solve these kind of questions. Okay, let's continue further. Now, since hydrogen atoms are replaced by substituting other groups or group of atoms or group of atoms on them, there is a possibility. In the cyclic molecule above, we have a hydroxyl group and a amine group introduced to the ring. Let's consider the carbon atom bonded to hydroxyl group first. Now, we are going to consider this one first. This carbon is also bonded to a hydrogen atom, and we never show this hydrogen atom as a part of skeletal formula. The other two groups bonded to it make up its four single bonds are not the same. This part is not the same as this entire part. Okay, so take it as imagine traveling around a ring in a clockwise direction from this carbon. You come to four carbon atoms, each bonded to two hydrogen atoms. Then you come to the carbon bonded to NH2 group and one hydrogen atom before arriving back when we started. We can think of this as this group. After that, travel around the ring in the opposite direction, and you will, in anti-clockwise direction from the same original carbon atom, this fourth bond from the carbon atom will be attached to this group. Okay, so it's a little bit different. So the original carbon atom has four different groups bonded to it. That's how it works. So they want you to take a stroll from this side towards this side clockwise, or this side to this side anti-clockwise, and you'll find these are different. When you find this, it's pretty easy to understand that this is actually a chiral carbon. And that's what he explains at the bottom. I'm going to clear all of this up. A hydrogen atom, an OH atom, one side clockwise rotation gives this, anti-clockwise gives this. This kind of tour tells you that you have a chiral center. Now, if you do the same with this one, go about this one. This is the one when we move all the way to here, or when we move all the way to here. These are different. Now, what they want you to do is to think about the other example, this carbon also connected to a hydrogen. Now, this would be the clockwise route. This would be the anti-clockwise route, different on both ends. So of course, this is also a chiral carbon. All right, that's how we finalize chiral carbon. So there are two chiral carbons in this structure. Make sense? Now, I have already given you the practice book. I've uploaded that to a site and I've given you the link. If you open up that book, the MCQ chapter has a lot of chiral carbon questions. Go through those questions. They're not connected in one place. Of course, you might have to skip a few questions in between before you land on a question which is related to chirality, but you can find a good number of chiral carbon questions that you can practice with. Okay, so symmetrical substituted cyclic molecules will not have a chiral center. Starting from carbon atoms bonded to the group substituted into the ring, you'll find two identical groups going around in both the clockwise and anti-clockwise directions. Therefore, no carbon atoms has four different groups to attach to it. Now, symmetrical means the one which carries symmetry. Now, if this was something like this, let's say, if this was something like this, then for this carbon atom, it would have symmetry. NH2 all the way NH2, NH2 all the way NH2. This would be symmetrical for this carbon, and this carbon would be non-chiral. We also use the term achiral. That's fine. Or this would be symmetric. This cannot be considered as asymmetric carbon. Make sense? It's important that you make good sense out of these kind of questions, or even if you don't make good sense now, after practice, you should get a good sense of it.
Yes, sir.
All right, good. Okay, let's move on. Now moving on. Indicate the wrong options, and then we can come up with the answer. So go ahead. I want you to work around this molecule and think that which of these choices, A, B, C, or D, would be correct. So how many chiral centers are present over there actually? Take your time.